Okay, so welcome everyone to our fourth session of the Foundations of Data Science of Machine Learning tutorial. Today it's my pleasure to introduce Ozan Öktem. Ozan Öktem is a professor of mathematics at KTH for about 8 years, I think. Ozan received his PhD in pure math at Stockholm University, and then worked actually for quite some time in industry, full-time job in industry for about 12 years. After which he returned to academia, to KTH, where he is a professor now, and he is also since 2016 director for the KTH Life Sciences Technologies platform, which is one of 5 strategic initiatives at KTH for coordinating multidisciplinary research. And so this is really very much also, I think it gives a good picture of the type of research that Ozan is doing. He is very well known for his work in inverse problems and inverse imaging problems, developing both theory, mathematical theory and methodology, particularly in the context of tomography. And here, I think one of his specialties, one of the things that I at least got to know Ozan was via his work on electron tomography. There are not a lot of really mathematically rigorous exposés on electron tomography out there, and Ozan's is one of them, or one of the maybe the only one. So in the last, I would say 2 or 3 years, Ozan got more and more interested in developing machine learning, deep learning based solutions for solving inverse problems. So that's this data-driven methods for inverse problems title. And again, he has actually written some of the seminal papers in this area, in this quite young subfield of inverse problems that many people are at the moment expanding upon and investigating further. One of them are these unrolled learned iterative schemes, learned primal dual, learned gradient descent. So I had the pleasure of writing a paper, an actinomerica paper with Ozan, Simon Erich and Peter Maas last year, which was a pleasure. And so building on this, Ozan will give a talk today, giving an overview of data-driven methods for inverse problems. In particular, I believe focusing on the Bayesian interpretation of using deep neural networks to solve inverse problems. That's where I guess I hand over to you, Ozan, just to tell everyone again, if you want to ask a question, please do so. And if you want to do this, raise your electronic hand and we can unmute you, preferably at the end of the talk. But if there is a very urgent question, I'll try to stop Ozan and you can ask the question in between. Okay, so Ozan. The word is over to you.
Okay, thank you very much, Carola, for the very generous introduction. And as Carola mentioned, this is actually the work of many people, not by far means not by me. I have the privilege to collaborate with some excellent people at KTH in Stockholm, some of which have actually left KTH by now. And likewise, with Carola and also Simon Erich was mentioned, and also Peter Maas were mentioned by Carola as international collaborators, as well as when it comes to the data side. Joost has done tremendous work at his group at CWI in Amsterdam. So this type of research is, of course, very hard to pursue just on your own. In that sense, you're really dependent on good collaborations. Okay, getting over to the topic of today is data-driven approaches for solving inverse problems. And I know that most of you are well aware of what an inverse problem is. I'll do this very quickly. Essentially, we want to recover a model parameter and we are given indirect observations of it. So this roughly amounts to running a simulator backwards. And this pops up in a variety of situations in society and also in sciences. And why are inverse problems challenging? Because they typically are ill-posed, which, if I phrase it a bit vaguely, would mean that if you try to maximize consistency against observed data only, you typically end up with an ill-posed or unstable solution, which means that a small change in data implies a large changes in your model parameter. So it's not enough just to match your observations of your indirect observations. You need to do something beyond that. And then, of course, the large-scale nature. Some of these inverse problems, typically those in imaging, or even after a clever discretization, they tend to result in very high-dimensional arrays. Of course, regularization is the broad notion of mathematical techniques to handle ill-posedness by balancing the need to fit observed data against avoiding overfitting. So data likelihood would be the model to generate how you generate data from the model parameter, essentially our simulator. And the prior model refers to one way of characterizing what you mean by a natural solution or natural model parameters. Well, being a bit more formalizing this vague or intuitive notion of inverse problem, probably the most common way of doing it is by looking at it as an operator equation. So here you typically have two spaces, capital X, which is the possible model parameters, and capital Y, which is your possible data. These could be some suitable inner product spaces, or typically they are infinite dimensional in the mathematical idealization. And your data is then an object that lives in data space, and it can be seen as a sample of a random variable. And here it's, of course, you have an A here, which is a mapping that takes a model parameter as input and produces the data. So that's our forward operator. And it acts on this unknown model parameter that we want to recover. So this is the very classical way of formalizing an inverse problem. And if you don't care about the statistical properties of this observation noise, only about the size, we are really down to the functional analytic viewpoint on inverse problems. If you're more careful about accounting for the statistical properties of the observation noise, then you're moving more towards statistical inference. You can now start discussing how to use machine learning already with this formulation of inverse problem. But as Carola indicated a bit, you actually have more flexibility in how to use machine learning if you adopt a more broad interpretation of an inverse problem, or more general interpretation. And in particular, what we're going to do is that we're going to also assume that the model parameter, which is in the context of imaging, this is the image we want to recover, that this guy is also generated by a random variable. And when we do that, you very naturally end up in a Bayesian formulation, which essentially reads like this. So here we added a prior model. Now suddenly X star is not just a deterministic quantity. It is, well, in fact, it is a deterministic quantity, but it's also a sample of a random variable, which has some prior distribution. And then now we, of course, we rephrase the task. We are now not looking for a solution. We're actually looking for the probability distribution of solutions conditioned on your measured data. The A operator is still there. The read-out noise is still there. So the only difference is that the randomness is not only in the data part, it also enters into the model parameter space. Of course, with this viewpoint, it's very sensible that if you're looking for the posterior now here, it's very tempting to resort to the Bayes theorem, because typically the data likelihood is known, or should be known at least. It is typically given by the forward operator and knowledge about the observation noise. And if you also in particular happen to know the prior, which is a bit of a more shaky assumption, then you could in principle use Bayes theorem to compute the posterior. There is a Bayesian regularization theory that has really been developing, I would say, quite rapidly the last 2 decades. I mean, tremendous advances have been made in the field. That is dealing with theoretically understanding the properties of the posterior in this setting. And in particular, it looks at what happens asymptotically as the noise term goes to 0 here. We'll get back to that in a second. But if you go back to the applications, and typically imaging applications, which I've been working quite a lot on, there is something that you quickly observe here. This idea of computing the posterior might sound very good and very tempting in theory, But you quickly end up with a computational feasibility issue when you move to imaging problems. But I here to give you some figures from clinical medical imaging. These are just clinical data in the sense of the problem size. Typically in medical CT imaging or tomographic imaging, the X here is a function on R3, which is a 3D image representing the interior anatomy. And just discretization would typically correspond to about 250,000 voxels, or these are the now unknowns. And likewise, the data that you gather in a clinical scanner is about 800 million dimensional array, roughly. And then the forward operator is a linear integral transform after logarithmic transformation of data. So you see quickly that these are huge dimensional arrays, and even recovering the posterior is typically out of the question. So what you do is that you either settle for computing a suitable estimator, preferably one that is somehow summarizing the posterior, like the mean, for example, is not such a bad one to choose, or another estimator if you would like so, or alternatively to generate samples of it. So what we're going to talk about today in this tutorial is more how you can use deep learning to do both of these alternatives. But turning back to the theory a bit, because I haven't done any that much at all. I mean, nothing actually, honestly speaking, on pushing the regularization theory for Bayesian inversion, but the theory has done quite a nice advances, so it's a bit unfair not to mention those. So I'm going to make my honest 2-minute attempt at doing that. So going back to the original inverse problem in the Bayesian setting, where you really go for the posterior, and just disregard for the time being all computational headaches. Just think of this as a theoretical question. Of course, existence here roughly refers to the situation where the conditional distributions for these conditional random variables exists at all. So essentially, this is the distribution of, in the context of images, X is the random variable generating images. So this is in the images conditioned on the measured data, and this is the data conditioned on the image inputs. Now you can show that these actually do exist under rather weak assumptions. Actually, you need to assume something about A, but not much. So existence is not really a big issue here. What about stability then? I was talking about that the classical inverse problem was unstable. There is even a Hadamard characterization of that in the functional analytics setting. So what about stability in this context, which essentially means that when is the posterior continuous with respect to variations in data? Of course, for that, you need to make sense of what you mean by continuity in the space of distributions, probability distributions. But assuming that you pick the right prior, that's an assumption, the posterior actually is stable in most cases. And in fact, continuity refers here to Hellinger well-posedness, which means also that the posterior moments are continuous with respect to data. So if you would try to compute the conditional mean, for example, solution, the average image, for example, in tomography, conditioned on your actual measurement, and you happen to have access to the correct prior, then you'll be definitely computing a stable estimator. Convergence, of course, is another issue. What happens? How does this posterior behave as the noise level goes to 0? You could actually show that it's actually constant. I mean, you would like to pick a, you can investigate when this would concentrate around the ground truth solution, which is still there, right? We still have a ground truth solution, which is unknown. This is called posterior consistency in this lingo. And then you could also, but this is not enough to discriminate priors. Ideally, you want to pick a prior where this concentration is as fast as possible. There's been a lot of work going into how to determine the so-called contraction rates. Okay, and to give you some flavor of a result taken from relevant to X-ray tomography, where A is the ray transform. I was just showing this integral transform a couple of slides ago. Assuming you have a Gaussian prior and assuming you have a Gaussian additive noise term, just look at the first line here. You could show that the conditional mean estimator, the difference between the conditional mean estimator and the actual conditional random variable, converges, or the action of it on a test function converges almost surely as the epsilon, which is the noise level, goes to 0, so the mean is 0, but there is a variance term. And of course, for those of you who know tomography, we know that limited angle tomography, for example, is much more ill-posed than when you have full angular coverage. And this will manifest itself here in the variance term blowing up, so to say. So this also captures this, asymptotic characterization of the posterior, also captures the ill-posedness that you get from the limited angle aspects. Okay, but I will be leaving the theory in the sense that this is just a summary, essentially a translation table between the functional analytic notions of regularization and those from the Bayesian inversion. And to summarize, there's a lot of nice, beautiful work done in Bayesian regularization. It's, I would say, fairly well developed for linear inverse problems or linear forward operators. And there's a lot of ongoing work for non-linear forward operators, typically motivated by PD parameter estimation. But the theory is nevertheless primarily concerned with what happens when the noise term in data goes to 0, in which case the choice of the particular prior should not really be that critical. In fact, much less is done, to my knowledge at least, for a setting where the noise level in data is fixed, or when the prior is misspecified, because you hardly know the right prior, right? And this becomes an issue if you don't let the noise level go to 0. So, as I said, it's the computational side of things is a different ball game. So this is what's going to be the main concern for the remaining part of my time. I wanted to give the theory side at least to give you some idea. There is unfortunately not that much connection yet between the deep learning based approaches, for example, for computing, let's say the conditional mean, and approaches for elucidating the theoretical aspects of Bayesian inversion. But this is definitely a good opportunity for young researchers to go into. So let's go back to the simplified inverse problem now, where we don't try to go for the entire posterior, but we settle for a suitable estimator. So deep direct estimation essentially refers to the idea of using deep machine learning, or typically deep learning, to learn how to this estimator from training data. So typically what you need to decide on is what type of training data do you have, first of all, to begin with. And then how do you set up your learning problem? These two things together essentially imply the type of estimator you're trying to compute. The next question is, how do you compute your estimator? So the first problem, this first part actually doesn't at all involve machine learning at all. It's essentially decision theory, statistical decision theory applied to inverse problems. This part is more about how to compute it, not what to compute. You need to typically choose a neural network architecture, which essentially means you're parameterizing the family of estimators you're interested in. And then you need to train this neural network against this training data, once you're trained, keep in mind that this is an important distinction. When you have trained your neural network, you don't have a reconstruction, you have a reconstruction method. So the result, the output of the training procedure is a reconstruction method. And for those of you who listened to Weinan E last week, he was giving a nice survey on the mathematical foundations of deep learning. He was essentially listing 3 basic steps that supervised learning involves. He was saying that one needs to decide on the hypothesis space, which essentially is the choice of the architecture for the neural network. He was saying that one needs to choose a loss function, which essentially means you decide on which learning problem you're solving, which essentially means you're specifying the estimator you're computing. And he was mentioning that you need to choose an optimization algorithm and the hyperparameters for doing the training itself, which essentially means train a neural network. So this is his way of stratifying how to use machine learning in scientific problems or problems in general. I'm just trying to relate that to today's talk, so to say. So which type of estimators can then you compute with machine learning or deep direct estimation? Directly try to approximate the estimator, so to say. Well, as I said, it depends on the type of training data you have. So if you have supervised data, you could try to compute a Bayes estimator, which in particular includes the posterior mean, if you choose the loss function appropriately. Keep in mind that X here is in tomography would be the set of 2D, 3D images, and Y in tomography would be the set of possible tomographic data. So these are very high dimensional spaces. If you have only unsupervised data in the model parameter space, that is just a bunch of images lying around, for example, then you could try to compute the map estimator with a learn prior. If you have unsupervised data, just a bunch of tomographic data lying around, then you could use deep learning to compute a map estimator, which is handcrafted by all means, not a learn prior or anything like that, but you're using machine learning to compute optimization in a faster manner. And finally, if you have unpaired data in X and Y, then there's a bunch of estimators that you can compute that are given by generative models that we won't be able to have so much time to touch on these, but worth mentioning at least. So I'm going to talk a bit more detail about the first one, which is, let's go into that one. How do we compute the posterior mean then? So our problem now is to compute the mean image. If you talk about imaging here, we want to compute the average image conditioned on your measured tomographic data, which we assume is generated by a stochastic model, which is given like that, where there's a forward operator, which acts on the ground truth image, which we don't know. That's what we want to do. And of course, the approach is, of course, to use machine learning. So what we have at our disposal is a bunch of training data points. So we have a bunch of images and corresponding CT data, if we were talking about tomography. And these are samples generated by this joint random variable. And so these are roughly fulfilling this equation here. And then what we do first is that we make a quick theoretical observation. We see that the conditional mean or the posterior mean can be rewritten in this way. Now, this is for those of you who know about statistics, you would recognize the right-hand side as a Bayes estimator. And this actually, honestly speaking, looks worse, right? Because here, the expectation is over the posterior, which we don't know. Here, the expectation is over the joint random variable distribution of images and data, which we don't know either, right? And on top of it, there is an optimization here over all possible reconstruction methods. Each R here is a mapping from data to model or image or model parameter. So each R is a candidate reconstruction method. We are looking at all possible reconstruction methods, essentially within some class. And then we are picking the one that is, in this context, has the minimum average L2 loss. Now, clearly, this expectation is unfeasible. We don't know the joint distribution. And even trying to compute this by some Markov chain Monte Carlo or something like that would be prohibitive from a dimension point of view. So, but we have the training data, right? That's what we have. So I would say if you have enough training data, you could replace this expectation by this empirical counterpart. So roughly, and then next, we don't look at all possible reconstruction methods. We look at a certain subclass of reconstruction methods that are parameterized by some finite dimensional parameter. Now, theta is not a scalar. I want to point that out. It could be quite a high dimensional parameter, but nevertheless, it's a parameter. So suddenly this infinite dimensional optimization over this horrendous objective looks slightly more tractable at least. And this is something that anybody who's done supervised learning will recognize as this is just a standard formulation for supervised learning. Now, unfortunately, this approach will not work in tomography, very much for the reason that due to the dimensionality of the problem, you would need an astronomical amount of training data to make this work. So you need to be a bit more clever. And in particular, it's about how you choose your parameterization. Because you see, we know a lot more here. We know that the data, we know a bit about how data is generated, right? We have a forward operator, we have a noise component and so on. So with this approach so far, none of that is accounted for explicitly here. Of course, it's all implicitly embedded in the training data, but that's maybe too weak, right? So why do we try to learn something that we already know? The idea here is to choose a domain-adapted architecture that is to adapt the parameterization of the reconstruction method to include at least information about an explicit forward operator and also preferably the adjoint derivative of it. And this is what Carola was mentioning, unrolling quickly in the introduction. And unrolling is one way of doing this. Not the only way, but one way. We'll come back to that in a second. So I need to be a bit cautious about the time. So I'm just going to actually skip the other approaches, unfortunately, to save some time. And I might get back to them. These are when you have, depending on the type of training data you have, you can compute different type of estimators. We just did the example with the supervised data where you have paired data, which is the one that I'm going to show examples from. So I'm going to skip this and move on to the unrolling idea. So one thing is, of course, which estimator do you want to compute? Here it is the conditional mean that we are targeting. The question now is, okay, fine, I'm going to compute the conditional mean. Now I need to do this more pragmatically. I need to pick a deep neural network architecture that's adapted to my situation. And this kind of brings us to a subfield of machine learning, which is very young. I mean, the whole machine learning field is, people say it's old, but at least the recent surge is not that old. And the scientific machine learning is even younger, I would say. So essentially it tries to merge the ideas from scientific computing, where you typically have handcrafted domain-specific models, classical applied mathematics, PDEs, and so on, with ideas from machine learning, where you do data-driven modeling. And a big portion of scientific machine learning is dealing with which deep neural network architectures do you use. But typically what you want to do is that you want to use a network architecture and perhaps also loss function that incorporates a priori known symmetries, equivariances, invariances, or even models. You know, for example, that the ray transform has a certain equivariance property with respect to rotation or stuff like that. So can you build in these symmetries or invariances or these properties into the network architectures from the beginning, or also the loss functions? This is a big topic. And unrolling is a framework for assembling neural networks that approximate operators that are defined by iterative schemes. So if you have an operator that is mapping between two spaces, and this operator is given implicitly by some iterative scheme, then you can use that iterative scheme and make it part of you can actually essentially create a deep neural network out of that iterative scheme by unrolling it. We will come back to that in a second. And this can be used, of course, to solve PDEs if you want. These are some example references taking that approach. You can use this for the operator that is given by the solution of a convex optimization problem. You could address in a similar manner. Or in case of inverse problems, what we want to do is that we want to have a deep neural network that approximates A inverse, or a regularized version of A inverse, maybe I should say. And we know explicit information about the A and also preferably the derivative adjoint of A. These unrolled schemes also go under different names. They are sometimes called physics-aware neural networks or recurrent inference machines, or yeah, here you see other terms that are sometimes used for these unrolled schemes. Now, to give you an idea of how unrolling works without writing formulas, here's an example of an iterative scheme. That is, the top row is the data space, and the bottom row is the reconstruction model parameter space. And typically, this iterative scheme would iterates between the data space and the, in this case, of tomographic imaging in the image space, back and forth like that. And this will, of course, go on, typically in the limits. It will, and assume that these updating rules that are in between here, here A is typically used to map from the data, from the image space to data space. And if A is linear, you can talk about the A adjoint directly, and that you use to map back from the data to image space. and if these updatings are typically chosen carefully so that this whole thing would converge to some suitable approximation of A inverse. Well, the whole idea of unrolling is, without writing any formulas, is to merely replace these updates by deep neural networks. That's it. And while doing that, you also stop it. So you don't, if the regular scheme would go on forever to the right here, You just break it, stop it brutally, and you replace these updating schemes by convolutional neural networks in this case. While you're training this entire thing end to end, keep in mind that the A and A stars that are encoding the physics and maybe the boundary conditions, all that information is embedded in A and A star. These are handcrafted, these are not learned. But these CNNs that are almost acting as denoisers in the data and reconstruction space, these are the things that you're training. Now, I know that LDAT likes more formulas, so I'm also trying to present this idea in formulas instead of images. So take an even simpler iterative scheme that would typically solve this least squares type of problem. You would do a gradient descent, right? And if A is linear, you would do something like that. Now, if you stop this iterative scheme after just maybe a few iterations brutally, and then there is no, it doesn't make sense to do the updating precisely in this manner. So you're replacing this precise updating rule by a convolutional neural network. And that is the idea of the learned gradient descent. There's nothing more than that. You stop the iterate after n steps, and n is capital N is a small number here. Think about 10 or something like that. And then you're replacing the very handcrafted updates with a convolutional neural network. And since this thing stops after 10, let's say, unrolled iterations, you have a well-defined operator that maps data into reconstruct model parameters or images. And then but it depends on this high-dimensional parameter. And then you train the whole thing end to end. And this is essentially the image illustration of what this learned gradient descent scheme would look like. Okay, and then finally, this is the computer science way of visualizing it, but I skipped that because I know that many people don't like to understand neural networks in this way. So let's see how this performs for tomographic reconstruction. Tomographic reconstruction essentially means we're going to do it super simplified setting first with a 2D Shep-Logan phantom. It's a step function. And then we're going to do an example which is more clinically relevant. In this very simplified setting, it's highly undersampled. So the number of data points is around 5,500, and the number of unknowns is 16,500, roughly speaking. And we are very generous with training data. We have 50,000 pairs of 2D images and corresponding 2D parallel beam tomographic data. Well, here is the ground truth. This is one example of the training data used for training the networks. These are random ellipsoids that are just randomly sampled. And applying now filter back projection, which has nothing to do with training, will give you something like that. TV regular total variation, which is very well suited for this type of object, is performing like this if you pick the optimal parameter for it. If you do now denoising afterwards by using machine learning, you try to fix the deficiencies of filter back projection with the machine learning approach. You can do that too. You get something like that. And if you now do the unrolled deep neural network and reconstruct by this unrolled scheme, you get something like this. Now, in this example, it's so you can also compute the conditional mean by Markov chain Monte Carlo techniques. And here we have the luxury of using the true prior, because when we have been generating this training data, we have assigned a synthetic stochastic model. So if you do that, you get something like that. Okay. So clearly, this is the best. Of course, time-wise, this takes for ages, the bottom row. But you also see that even compared to total variation on this simplistic 2D case, undersampled 2D image, you gain quite a bit of PSNR. And also the number of parameters in the network is 250,000 here, whereas the denoising approach has 10⁷ parameters. FPP and TV has one parameter each, which you select, and the conditional mean MCMC estimator has no parameters. But this was a toy example, so let's move on to a bit more realistic example, which is more clinically inspired. Here we have Poisson data now. This is now fully sampled, regular clinical sampling. You have about 10,000 angles, and one detector rows is fan beam data, 1,000 lines per angle. So you have 1 million data points. You still have 250,000 unknowns. You are oversampling here. Now we only have training data from 9 patients. Still gives us 2,000 pairs of 2D slice images at corresponding fan beam data, but it's only from 9 patients. And the noise is Poisson noise. It's quite a high noise level in data here, actually. So this is the challenge here. Okay, this is the ground truth, and this is the data that you see to the right. And since you guys are not radiologists, I think I'm just going to help you a bit. So we're going to look at this region, which is should be kept homogeneous, and then we want to preserve this little black dot here. Filter back projection performs like this. You have false features that are equally pronounced, like the true one here. You have the streak, which is well known, of course, due to the sampling aspect. If you do total variation, you get something like that. It gets better PSNR and so on, but the streak remains. This false feature remains. The true one is still there, right? If you do the denoising part with a deep neural network, you perform something like this. I don't know if it's better or not, but still the streak is there. The bed is more visible. That's perhaps good. The false feature is more pronounced. You have almost washed out this true feature. Now, if you wonder what it means to include the physics or not in the deep neural network, think of it as the difference between this reconstruction and the next one. So by including the physics, we can remove a global artifact, because the streak is not noise release, more like a sampling type of artifact. So we get rid of the streak, and we managed to preserve this darkening there without introduce and remove the false one up here, for example. And of course, timing-wise, the run times are quite acceptable here. The training takes 4 ages, takes a day and a half or 2 on a decent computer, but run times are actually quite fast. Once trains is fast. It's one fun exercise is to look at how does the reconstruction behave as we move across layers. In this case, we had unrolled 10 layers that I was showing you when I was showing you this reconstruction here. We are doing unrolling of 10 primal dual iterations in some sense. So there are 10 unrolled layers. So this is the reconstruction after the first unrolled layer, and then we move here to the second. Not much is happening really. What's up here between second and third? Not much is happening. Not much is happening here. And then some edges are becoming more pronounced, and then here now things are starting to happen. And finally, now we are seeing some differences. And in particular, at the very end here, wow, between 7 and 8, a lot of things are happening. And then the finishing line is not much is happening. And this, for those of you who saw the Eldad's talk last week, that was a classification example where he was showing the dynamical systems type of behavior. It seems that the network is almost like doing nothing in the beginning, and then it gets its act together and does the work towards the end. It's almost like a teenager postponing whatever he or she has to do until the very end. And this is a very different behavior from typical numerical methods, where you would typically see the improvements early on, and then the method is struggling to get the finer details at the very end, which shows some quite interesting differences. Now, I was thinking on reporting about some ongoing work, but I'm running out of time, so I'm going to skip that and go directly to computing sampling from the deep neural network. So far, we have used deep neural networks to compute a single estimator, which essentially gives us a reconstruction method which produces one image. Okay. So what if we can one compute, or can one use deep neural networks to compute not a single estimator perhaps, but to sample from a posterior distribution? And that's the idea with the remaining 10 minutes is what I'm going to devote my time to. So the idea typically is that you might have heard about, some of you might have heard about deep fakes and so on in the media. where people can put their faces or even sound and mouth motion and so on. You just need a photograph and then you can take an arbitrary movie almost and paste a person into that. So these are quite, let's say, I would say quite impressive. Image processing tasks are typically done by generative adversarial networks. The idea there is to set up a game, minimax type of game between you're pitching two networks against each other. One is trying to generate data that looks like the training data. You have some training data, which is some random draws from some high dimensional distribution. And the generator tries to mimic data from that distribution that is unknown. And the discriminator tries to discriminate whether this is a good sample or not. And the conditional GAN is to do this in a conditional setting, because when we're doing image problems, we're naturally dealing with conditional distributions. And so the posterior sampling essentially is to use a generator, which is a trained conditional GAN, or a generative adversarial network. And this trained conditional GAN is used to sample from the posterior, unknown posterior in an image problem. You could see it for those of you who know quite a bit of, let's say, non-parametric Bayesian statistics. You could see this as a variant of variation-based methods, with a learned approximation of the posterior, not a handcrafted approximation. Okay, so to explain the approach, here's the deal. You start with supervised data, right? That's our setting. So you are given samples generated by the joint distribution of this. So X is generating in tomography images and Y generates data. And this is the unknown distribution. Now we are interested in generating samples from this random variable, which is the images conditioned on the data. You set up this optimization problem. You say, oh, if I knew the posterior, then I could have a parameterized family of probability distributions. I call them the generator. And I'm looking among all of these guys, I'm picking the one that is closest to the posterior in some sense. So the W is the distance between the probability distributions. And I'm minimizing the average discrepancy, so to say. The problem, of course, is that the posterior is unknown. So this formulation doesn't quite make sense, perhaps. So what do? Well, we pick a certain distance here, which is a cleverly picked one. It's the Wasserstein 1 distance, actually. And then we use the Kantorovich-Rubinstein characterization of that distance. And this allows us to reformulate this unfeasible method here as a minimax game. So this is a new formulation. We suddenly introduced this discriminator now, which is a mapping. So the posterior distribution is gone. It's replaced by a discriminator. The generator is still there, right? We're still sampling from the generator. So essentially, and then we are maximizing. So this is the minimax formulation of the same problem. This is equivalence. We can prove that this is equivalence. Now this optimization or the supremum here is quite unfeasible computationally. So we, of course, parameterize the Ds by deep neural network. Those are next. The joint law in this expectation is also unknown. The posterior was unknown. So in particular, the joint law is unknown. But we have supervised data here, up here. So we are replacing the empirical distribution. We're replacing the expectation by its empirical counterpart. And then, of course, it's difficult in a computer to parameterize parameterized family of probability distributions. So we are replacing that with a function which has a random input. So with all these changes, we have a formulation of a learning problem, which is perhaps suitable for supervised learning. Well, in fact, this is not going to work either, because in an inverse problem, what typically happens is that you only have one single, in your training data, for each data Y, you only see one example of the ground truth, let's say, image. So if you would try to train this as it's written, it will degenerate. It will lead to what is called mode collapse. So essentially the generator, which you're, at the end of the day, you want to have the generator here, which is mimicking which you are using to sample from the posterior, it will essentially it will just return back to you what is seen from the training data, which is highly undesirable. So you need to do a lot of tricks. I run out of time totally. This is the indication I run out of time. So I will simply go on and wrap up here. You do some engineering tricks. I'm sorry to wrap up, and you can handle this. So let me do the following. Let me show you how this. Here is actually an example. Again, tomographic data, very noisy undersampled case. This is the ground truth. This is FPP. This is conditional mean. This is one sample from the posterior, and this is total variation reconstruction. So again, here you can see, here's the phantom, this is filtered back projection, and this is one sample from the posterior. But if you get,
Ozan, just take another couple of minutes.
Thank you. I just did 2 or 3 minutes.
Yeah.
So of course, if you have one sample from the posterior, this might look a bit impressive, but of course, if you take another sample from the posterior, you see that this thing is changing. And of course, this is not so fun if it's changing like that. So you typically wouldn't present a single sample as a solution. So what you do is, of course, that you can compute the mean. If you do that, you get the conditional mean in some sense, right? It's computed from 1,000 samples. But you can also now compute the standard deviation, point by standard deviation, for example, or you could compute even covariance if you want to do that, and so on. So this kind of opens up for different ways of doing image reconstruction, where you really sample from the distribution of images conditioned on the data, which has been really, to my knowledge, not been feasible computationally before. Now, I'm going to conclude my last 3 or 4 minutes with a case from a real clinical case. This is a case where the patient was referred to the clinic with a suspected lesion in the liver. And of course, they took a regular CT scan on the guy. But to make this example extra hard, we're going to go to the ultra low dose regime. We're going to take 2% of normal dose. So we keep the full angular sampling, but we have so much noise that it corresponds to 2% of normal dose. With such bad data, which is to the left, and if you perform filter back projection, you get something that you see in the middle. Now, even the most seasoned clinician cannot see any lesion here in the liver. There's no way to do that. It's just simply too bad data. Well, if you compute this posterior mean from 1,000 samples, you get something like that. Now, the clinicians are good. I mean, these guys are really good. So they immediately spotted this slight dark. By the way, this is the liver, for those of you who wonder here. So they can see this darkening here, right? So you can narrow down on this darkening and say, okay, now given that the data is so bad, it's fair to ask yourself, how certain are we that this lesion really exists? And that essentially brings us to the case where you do, since we have 1,000 samples, we can compute the average intensity inside the encircled region with the average in the entire liver. And if this intensity difference is large enough, we just say there is an anomaly. We don't know if it's a lesion or not. We say it's an anomaly. And then you can do a histogram plot of that. And then on that, you can base a hypothesis test. And with that test, it will tell you that with 95% confidence, there is indeed a lesion. By the way, this is the ground truth. Well, the normal dose, there is no ground truth here, by the way, but there's the normal dose image where the lesion is clearly visible. Also, there's actually a happy ending to this story. This was a cyst and not a malignant lesion. So there was a good ending to the story here. Nevertheless, an important take-home message is that the size of the problem is that we still have a 250,000 dimensional image. I mean, the image is, of course, 2-dimensional here, but the array is 250,000 dimensional. The data is 1,000,000 dimensional. And this whole thing with the sampling thing, the generator and the discriminator is trained on 9 patients' data, extremely few training data sets. And once trained, generating a single sample takes 20 milliseconds on a gaming PC. The last minute, I just want to mention, I'm out of time now, so I'm sorry, Carola, you have to break me, but I just want to mention a couple of ongoing work that is in the field. So a lot of effort is going into combining and rolling with other aspects of architecture, network architectures. You might want to enforce invertibility. You want to have a scale separation or convexity, for example. You want to have a convex functional. If you want to approximate a convex functional, you want to make sure that your neural network is convex. Or I mentioned these equivariance invariance properties under a group action. There's a beautiful work in geometric deep learning that is dealing with that. And also, I'm also involved in, for example, from the analysis, we know that the microlocal properties of the operators, we know beforehand how we expect singularities to be transformed. Can we enforce that on the deep neural networks as well? The choice of loss function, I'm not going to mention so much on, I'm already out of time. Also, you can do dynamic inverse problems by learning how to do diffeomorphic deformations. You could even learn corrections to the forward operator. And nevertheless, there's a lot of new theoretical analysis specifically for these unrolled schemes. So I think I should stop here. I think also to take the opportunity to make quick advertisement for the 2 forthcoming talks, which I believe will touch a bit on also other ways of constructing domain-adapted neural network architectures for specific inverse problems. With this, I think I should be, I'm done. So I will stop sharing my screen and just share a little movie quickly that shows you a random walk through the posterior landscape. And I'm done. Thank you very much.
Thanks a lot, Ozan. Thank you so much. So we are ready now to take questions. Once I figure out how I go back from your movie to my view. Yes. No, that's fine. That's fine. I figured it out. Yeah. Okay. So we have one question from, let me just see if I can, Saloni, if you want to ask your question, maybe you can raise your hand because then I can, wait, I'll look for you. Okay. Okay, thank you. Okay. Did you, okay, 1 second, I'll just, this is technologically not so easy.
I can allow her to talk.
You can allow her to talk? Good, please do.
I just did.
Saloni, you can ask your question now.
Hello. Yeah, am I audible?
Yes.
Yeah. Hi, thank you so much once again for the presentation and especially for the clarity, and it's an inspiring talk. I just had a very basic question regarding the unrolling. So we saw that CNN obviously is playing a very big role, and I was just wondering if we keep it constant or like what influences the CNN in the unrolling process?
I mean, the CNNs were essentially acting a bit as denoisers in image and reconstruction space, right? So if we go back quickly here, if I'm allowed to share a bit. Sorry. So typically, of course, nothing stops you from using a different architecture, but CNNs have been quite successful in dealing with images in general. And so, this is the one. There we go. Come on. So you see the CNNs here act both on the sinogram space, which is the CT data space, and also on the image space. So in that sense, the forward operator and the adjoint takes care of the global relationships, whereas the CNNs are more like denoisers. You can think of them that way intuitively. I don't know if that answers your question, but.
Yeah, I think I just have to think about this a little more. Okay, but yeah, thank you so much. I'll leave it for the rest to ask questions.
Maybe just to say, to clarify, Ozan, the CNN is in general changing in every iteration, right? The weights are changing, right? So
sorry, that was might not have been clear from the illustration. Each CNN comes with its own weights, which are typically, I mean, these CNNs in this example, they are like 5 or 6 layers. Each of these CNNs, small CNNs, are 5 or 6 layers. But then you have, of course, they are stacked in this unrolled scheme. So the whole thing becomes quite deep, and they have their own weights. There is no weight sharing going on here during the training.
Exactly. Okay. Okay. Can you unmute Thomas,
Yeah,
please, Ozan?
I can do this. That's it.
Thank you.
Thomas, you can talk.
All right, thank you for that talk and thank you for the presentation. Quick question on the, you made mention of the fact that the whole algorithm turns into a reconstruction method, or like the output of the neural network becomes a reconstruction. My question is it a reconstruction of a higher dimension into a lower dimension, or a reconstruction of the solution to whatever, whether PD or to the problem in question?
Yes, I mean, in this example, the idea was that the neural network should approximate A inverse, right? That's what you want to do, okay? So it would be a mapping from the data space to reconstruction space, model parameter space.
All right.
And if in tomography, that means you map measured tomographic data to images. But the training, the output of the training is this mapping, right? So when you're training, you're searching over all possible mappings within a certain class. But once you've trained, then you have a mapping which you can throw new data at, and hopefully you get a decent reconstruction out of it.
Okay.
Did that clarify your question?
Yeah, so it's not a dimensional reduction algorithm like Tolkien's theorem or something.
Not explicitly in that sense. No. I mean, you might have built in the network architecture, you could think of situations where you could do a unit type of thing where you do some reduction and then expansion again, but not conceptually, no.
Okay, all right, thank you.
Next question comes from Alberto.
Alberto, you are unmuted.
Yeah, good. Hi, can you hear me?
Yes, I can hear you.
Great, thank you both for the series and the talk. So I have actually a few questions. I don't know if I can ask more than one, but so they—
You can ask more than one, Alberto.
So the first one has to do with you know, how you started motivating the the conditional mean sort of as, you know, the minimizer of the L2 loss, so just the usual decision theory thing. So once you implement all of this, are you changing the space of estimators in there? Are you doing the minimization over? Are you changing the norm, like the L2 norm? And, you know, depending on the answer, what are you getting? Are you getting the conditional mean also conditioned on some transformations? You know, what are you, how does it change, you know, the decision rule?
That's a good question. So first of all, I mean, of course, the theory for this is, I mean, the interpretation of a conditional mean as a Bayes estimator is, of course, can also be done in infinite dimensional situation. But for computation, everything takes place in finite dimensions. In which case, the spaces x and y are just Rn and Rm, right, for large numbers and an m. We are looking at a parameterized class of estimators, right? So, or decision rules, if you may prefer that word. So which is parameterized by the deep neural networks, right? So this is it's a subclass of potential estimators that you're looking at, which you have a priori defined, and that's why you use your deep neural network architecture to do that narrowing down. But then, of course, the question pops up. Okay, when you do, I mean, the loss function that acts on the reconstruction space, it doesn't act on the space of estimators, right? So that is just, I mean, typically you take, I mean, L2 is not, I mean, you could pick other loss functions for sure, but L2 is a fairly generic choice in imaging at least. And so, but nothing stops you from using a loss that is more adapted to a task, for example, that you can do very well. But I would say, in general, I would say the loss function, I don't know if maybe I misunderstood your question, so I maybe answered.
I think the estimator changes, no? Doesn't it, sort of depending on the loss function?
Yeah, I mean, we are doing empirical risk minimization, right? That's what actually we're doing. And then how that exactly relates to the real estimator that you want to compute, that's a hairy question. I mean, that would essentially mean that you would like to estimate the generalization gap, ideally. And yeah, from a theory point of view, I think that's a very difficult question.
Okay, and then thank you. Can I ask you just on at the end that you were showing that you do the sample means
yes.
to get to get something that you show the clinician. Is it just the usual mean, like pixel by pixel, or could you do some Wasserstein as well, that somehow
this is the usual crude.
Right.
There is no more sophisticated shape related mean or anything like that. This is just brutal pixel by pixel mean.
Okay. And then the last question. So you mentioned at the very end in the references the paper by Zhang and Tao on guarantees for variational inference methods.
Yes. That was a vague hope.
Is this just sort of like a blunt prediction that it could be used, or do you actually have something that?
I don't have anything that it's definitely a blunt. I wouldn't even call it prediction. I would just something from the theory side that perhaps could be used, perhaps. Because a very natural question you ask yourself if you're claiming that you're sampling from these extremely high dimensional distributions, and this is a classical problem in statistics, for God's sake. So it's obvious that it's very clear that you're not. I mean, how well are you doing, right? I mean, that's the big question.
Right.
So this is all open questions, and this paper that from Zhang and Gao was actually recommended by Richard Nicol in Cambridge, and
yes,
could be perhaps could be of interest.
I mean, although that one is for it would be when the noise goes to zero in some sense, which is not what was concerned with. But
no. But I mean, we have to give the theoreticians
guarantee. Yeah. Right.
So
okay.
Alberto and Ozan, I think this is maybe also a discussion that could be continued later by email. Thanks a lot, Alberto. These were really, really interesting questions. There is one more question from Antonio.
Okay. Yeah, Antonio, you are.
You can talk, Antonio.
Yeah.
Huh? No, he can't.
Wait. He should. No, he should be.
No, yes.
You're unmuting me, like Alberto.
Sorry.
Hello?
Yes, Antonio.
Yes.
Okay, so thank you. It was a very interesting talk, so thank you for that. Towards the end of the talk, you mentioned that when you train a GAN, if you just train in a standard supervised problem, you're going to end up with mode collapse because of the way how the samples that we give it are paired. So I'm afraid I missed. How did you say that gets resolved to make it work, and why is that work?
I didn't show you, so you didn't miss anything. I just skipped that part because it's a bit technical, and also I was running out of time. So there were two reasons for it. First of all, I wouldn't maybe say that we solved it, but it definitely helps to. What we do is the following. We essentially you have to reformulate the whole approach and introduce another product space structure. You essentially not only look at the original pairing with the, in this case, image and the corresponding data, you also take the thing that's been produced by the generator, and you combine that with you also create new pairs where you essentially make up data, if I may say so, make up images, sorry. And in that way, you artificially, in some sense, you allow the discriminator to see more, let's say, more pairs. And to give a better explanation of this, I would actually do it offline. Actually, it's a bit requires some writing down formulas and so on. So if you're interested, either you can check out the paper, or I can have an offline discussion. Well, online. It will have to be online, but not in front of everybody.
So what was the paper reference again then?
Okay. Okay. Well, okay. Give me 1 second. I'll share the screen here. There we go. So let's see. There we go. This is the.
Okay.
This is the. If you just Google deep Bayesian inversion on our site, you'll find it. There we spill out all the details. There, everything is there. And if you're still wondering, I'd be glad to help out.
Thank you.
Okay, super. Thanks a lot, Antonio, for the question. Thanks a lot for everyone to join, and thank you, Ozan. This was really a great talk, gave a really good overview, and also showed what we mathematically, statistically at the moment also understand about these type of approaches and where the gaps are. So that was really, really interesting. Thank you. So we in this tutorial reconvene tomorrow, same time, for Rebecca Willett's talk on using deep learning to solve inverse problems, linear inverse problems. Okay, thanks a lot, everyone.
Thank you very much. Have a nice day.
Bye-bye. Bye. Bye.